Welcome back. In this assignment, we're going to dig in a little bit deeper with some of the regression, and in particular, we're going to go on to Chapter 5 of the textbook, where we're looking at this causal inferences with experiments. And what we're really saying there is that oftentimes we have a couple of variables, and all we have are correlations. And correlation says that, we have some sort of relationship here, but we don't know the cause of it. So we need to start looking at what are those variables that, that really could be causing this relationship to be there or not be there in the future. So what we're going to do in here, we're going to open up a new data set. The data set's going to come in from the Oregon Health Insurance experiment file, and it's data that you may see out there on the internet or whatever else. I have a OHIE results.csv file that's available for you so that you can go in. You're going to read that in, create yourself a file. I called mine OHIE is what I'm looking at. You can look at the dimensions of it. You can look at the header of it just to see what's in here. The Taddy textbook will explain to you what each one of these columns is, so you can go in and take a look in example 5.1 where it discusses these things. And then from there you can also take and it's kind of like a pivot table in Excel, and we just call it a table in R. So if I want to look at a table of my new data that I've just brought in, I'm going to focus only on the selected column here, and I put that in, hit enter. It comes back, like I said, as a pivot table. There are 11,790 that were not selected. There were 11,651 who were selected. So you can see here, what's going on. You can also see that what we're really looking at in this data set, our Y variable is the number of doctor visits. And the idea here is that, doctor visits are a good thing if we are looking at going to a primary care doctor so we can catch things earlier instead of later. So a visit to the primary care doctor typically would be regarded as less expensive than, say, if they had to go to the emergency room whenever something got bad. So again, most of the time the Y variable is going to be the document number. And then there are also some things in here like Medicaid and the number of people in the household that we're also going to work with. What we're thinking with this experiment that they ran in Oregon is that there were some people who were selected to go on Medicaid, and then they either decided to go on Medicaid or not go on Medicaid. The experiment, what we're really getting at the bottom line is, and we call it an average treatment effect in the book, ATE, we're really trying to say, is there a difference between whether or not somebody went to the doctor based on whether they were selected, which means that they were Medicaid eligible, versus whether they weren't Medicaid acceptable. And so the book here, it says, that one way I can tell that is I want to look at the Y bar. And you guys remember from statistics, usually averages had the letter with a line above it. And people may call it, X bar or Y bar. But this really says that basically what I'm looking at is look at the averages, or take the average rather, of everything that was in selected, everything that was in that was not selected, and what I really want to apply it to is the number of doctor visits. How many more doctor visits did people go on if they were selected versus if they weren't selected? Again, using the way the book puts this out, you ought to get somewhere around 0.25. That means that the people who were selected for Medicaid, on average, went to 0.25 more doctor visits than those who were not selected. Now, if we just did this as a regular regression model, we could have written a general linear regression model, let's call it FIT ATE, where I'm going to look at document number. I'm going to regress it on whether it was selected or not. Again, just one variable. And the data I'm using is my OHIE data. Once I run that, I can look at the coefficients of my fit ATE data based on selected. And once again, it shows the exact same number here, that it is 0.25 times more likely. And what that really is, again, from our regression, this is our beta, right? This is the slope. Regression model, it's just giving me the slope once again on what's going on. This is a y equals mx plus b model. Y is the number of doctor visits. Here's my slope. The x is 1 for selected, 0 if not selected. And so again, very easy for us to run a linear regression to see the exact same thing going on. All right, now 0.25 is what the data tells us. However, is it really 0.25? We talked about this in the in assignment number 2. What's the confidence interval? Is it really 0.25 or is it based on a sample? Well, of course it's based on a sample, so let's calculate a confidence interval here. If we do a summary of our model, fit ATE, it's going to once again show us 0.24897 is our estimate, but we have a standard error of 0.038. We remember that to calculate a confidence interval, what we can do is take our estimate, 0.25, minus 1.96, which is almost 2 standard deviations, which is what a 95% confidence interval is, times the standard error of 0.038. So the truth is that our effect size could be as low as 0.18. If we do the plus, it could be as high as 0.32. So our confidence interval on this treatment effect really says this is somewhere between 0.18 and 0.32 more doctor visits for those who were selected versus those who weren't selected. Okay, let's go ahead and move on to section 5.3 of the text. One of the things that we can also do is go in and look at controlling for a condition that's inside of our data that we think that may have an effect on us. For instance, if we go in and again we pull a pivot table based on the number of people in the household and selected. So again, it's a pivot table: selected, not selected, yes selected, number in the household, 1, 2, 3 or more. We can see that if we look at these percentages, the percentage of people that were picked to be selected is much higher for those that are in 3 or more people in a household. The book talks about how this happened and the way that the experiment was set up, so please take a look at the book. It will help you there. But we can take this data and say that, if we take 8805 and divide it by the total number of people that are just one person in a household, 8805 divided by 760, and there's a numerical error. I see that I should have put 7655 instead of 7605. So that's a mistake. But roughly 54% of the households who only had one person were not selected to be in Medicaid. Again, so 54% were not selected. Let's look at the twos. If there were 2 people, again, 2979 divided by 2979 plus 3944, I got that one right. 43% of the people who had 2 people in the household were not selected. And then finally on the bottom one, with 3 or more, only 6 out of 58, or 10%, weren't selected. So there does seem to be something going on here with this variable of number of people selected based on the number of people that are in the household. So let's go in and let's adjust our linear model now, and let's control for this household effect. And you can see it by putting in a new general linear model. We're still going to use the number of doctor visits. That's still our Y. We're still regressing it on selected, but you see here we're multiplying it or controlling it with the number of people in the household. Okay, so this is the way the formula looks whenever I'm controlling it. If I look at the coefficients come out now and say, okay, here are the new coefficients with this new model fit adjust. Again, looking at doctor number, I'm interested in selected, but I want to control for the number of people that are in the household. Equation 5.13 in your textbook is going to go through each one of these coefficients. But really what we're looking at when you go through and pull these apart is selected is our base model. That's whenever there is only one person in the household, okay? So when there's one person in the household, it says that the treatment effect is really 0.33. Similarly, if there are two people in the household, it's 0.33, which is this number, minus the 0.15, which is selected when controlling for the number of people in the household. So the treatment effect goes down to 0.18 for whenever there's two people in the household. However, look what happens to our treatment effect when we get three or more people. It's the 0.33 plus 0.87. So if there are three or more people in the house, then there is likely to be 1.2 more doctor visits per person per year. Okay? Again, so what we've done, we've regressed, we have controlled for the number of people in the household. Now that I've done that, let's go back because I have my standard error now it's been a bit convoluted with the equations, and you can once again see that in figure 5.13. So what I can do is I can go back to my model and I can use the predict function. So I'm going to take the average of the prediction of my model when the data frame is 1 based on the number of people in the household, and I'm going to subtract from that, again, this is the average, from the prediction of when the data frame was 0, again, controlling for the number of people in the house. So when you put this formula in, it comes out and says that the true effect size, based on whether or not you were selected and controlling for the number of people in the house, that the true effect size is 0.29. Again, the true effect size when I'm controlling for the number of people in the household has gone from 0.25, which is what it was before we controlled, up to 0.29 now. We can create a confidence interval for this by using the bootstrapping method. The book does go into bootstrapping, gives a pretty good discussion about bootstrapping in there. That started back in chapters 2 and 3. But what we're really doing with bootstrapping is we're taking all of our data, we're going to draw a sample from that data, we're going to run our regression on that data, and then we're going to take our raw data, dump it back in to the to all of our cases again, and we're going to draw another random sample from it. So what we're doing is we're doing this multiple sampling technique using our data. We start off with 28,000 rows of data, and we may go in here and we may take samples of maybe 500 of them, and we'll run this 1,000 times. What we're trying to do is we're trying to estimate by going in and pulling these smaller samples. We're trying to look at a couple of things. What's the average? What's our average effect? But then also, what's the lowest we've ever seen? What's the highest we've ever seen? So we're really creating a new average of these samples and collecting the standard error or the variance off of it. So again, the bootstrapping technique is listed in there. You'll also find that because of this bootstrapping, that there are some of the functions that are in there that you will need to go up here to your Packages tab. And if you click on Packages, you can either load packages, install packages, or update packages. And what you're trying to do is you're trying to go in and find the correct packages for the new functions. And the reason that we have those different packages is that R is an open source. There are people that have gone into the data frame and computations, and they've created a new item called, in this case, data table. Data table has some extra functions associated with it that aren't automatically loaded into R. And so what you have to do is you have to load the package data.table. You will notice in your code that it needs to happen because sometimes you're going to get this error code. It says, something like this. It'll say error in library data.table. There's no package called data.table. What that means is that in your current version of R, that package isn't loaded, or in your current session of R, it's not showing up on there. All right, so again, you'll have to go into packages, you'll have to load it to make sure that it's in there. All right, so once we've loaded it in there, you need to call up data.table, and you do that with a command library, data.table. It says, hey, come in here. I need you to start working on it. And then once again in the textbook in this new section that we moved into on bootstrapping, it says they're going to take and they're going to split the data. This is where I told you that they were going to make they were going to take a sample from our current table. So they take and they split it. Split is a function that you can only get to if you have if you have data.table loaded. All right. You're also going to see things like binder in here as a new function. And so some of these things like binder and parallel, and boot are only going to be in there if you have loaded those packages. Okay, once again, let's go down here and look at the way that we're going to put this in. We're going to create this bootstrap. We're going to call it get the adjusted ATE. It's going to be a function of the data based on the IDs and binder. Data, we're going to bind it. We're going to fit the general linear model again using the selected document number, right? Here's my Y. Based on selected, controlling for the numbers of people in the household. We're going to take the mean, again at the predicted, like we did up here before, and we're going to run this 1,000 times. When it gets through running, and it may take a few seconds for your computer to get through this because once again, it's taking a sample, running this 1,000 times, and once it finishes it, it's going to come up and say, your real effect when we control for the number of people in a household is 0.29. Okay? It was 0.25 when we didn't control. And if we do control for the number of people in the household, it goes up to 0.29. Also, in this, it gives us a standard error. So you can calculate a confidence interval from this bootstrap. We can say that, here's our average, plus or minus 1.96 times the standard error. All right. The book does the confidence interval using a get CI function. That may work for you. It may not work for you. And I'm not sure exactly where the that new get CI is located in which of the libraries. I couldn't find it. So you can calculate it this other way, and it may be loaded in yours. All right. Next thing I want to do is I want to look at the logistic regression one more time. The book talks about logistic regression in example 5.3 But I think the direction that the book takes it, again, just makes it harder than it needs to be. Because what logistic regression really is supposed to be able to do is it's supposed to predict whether something is going to fall into one category or another. Our data really is set up very well for this same problem. However, I want us just to go, instead of looking once again at what the book does, let's just look at whether or not, again, I'm going to do a logistic regression. I just want to look at whether or not I can predict the number of doctor visits is going to be greater than 0 each year if I regress it on everything, right? This says look at the number of documents, or the number of doctor visits that are greater than 0. So I'm going to have zeros or ones, logistic regression. Regressed on, this dot comma says regressed on everything. And again, I know that we shouldn't just regress on everything because we don't have any theory behind it yet, but let's just do it investigatively. Let's regress document number greater than 0, where I'm going to have ones and zeros on everything, use my data, family binomial, which is what logistic regression is. Once I hit that in, put this in, I can do a summary. It brings up all of the coefficients. Again, we didn't have that many in this one. And then it gives us an estimate. And then remember from these estimates that what we're really trying to get to in logistic regression are odds. You know, what are the odds that something is going to fall into one category or another? You can kind of get an idea also on which ones are the most significant by looking over here at the stars or the asterisks, because these are the probability numbers, okay? This is the probability that this item contributes to our overall model. Again, 3 codes, 3 stars basically said significance is 0. This is the probability that this happened by chance is almost 0. 2 stars, the probability that this happened just due to chance is 0.1%. 1 star says the chance that this happened just due to random chance is 1%. All right, so which of these matter the most to us? Well, here's a 3 star and here's a 3 star. Number of household being 2, that doesn't, that's not very attractive to look at it. But this Medicaid does seem to have something going on here. So what's kind of happening is it says the number of doctor visits we have is certainly related to Medicaid. So I might be able to predict whether somebody went on a doctor visit just based on whether or not they were on Medicaid. So let's take and pull that one just a little bit further. Now, if you go back to section 1.3.2 in the textbook, it says that what we're going to do is we're going to take this estimate and we're going to use the exponential function and turn that into an odds. So let's look at our coefficient here. Medicaid, 8.978 times e to the minus 1, which really is 0.8978, because e to the minus 1 means 10 to the minus 1. So we just move the decimal point 1 direction to the left. So if I take and do the exponent of 0.8978, I get the number 2.45. And what does that mean? It says that the odds are 2.45 times greater for someone on Medicaid to go to the doctor compared to someone who's not on Medicaid. All right? Based on our data, it says if I just picked somebody at random and said, are you on Medicaid? That there would be a 2.45 times greater chance that they would say yes if they were on Medicaid versus whether they weren't on Medicaid. All right, hopefully that gives you some good insight this week. We've tied in the regression. We tied in both the linear regression, we tied in logistic regression, and we got to control for something. And we saw some bootstrapping and got a chance to play a little bit more with this. So hopefully this helps you this week. Whenever you finish it all up, please take a copy of your R code and send it in to me. All right, good luck. Let me know if you have any questions.